So let's go through proof of both of these. So existence and uniqueness. Okay, of course we only need to consider A when the rank is positive. We took care of the zero matrix above. All right, so take A to be an n by n matrix with rank R positive. We know, as observed from the result from section 3.3, was it, that a factorization of A as a product of L times R, where L is a full column rank matrix and R is a full row rank matrix, exists. All right. In Theorem 3.3.14, we dealt with a Gramian product. That was where we took a matrix A and considered A transpose times L. Let's go back and look at that. It looks like it's part 5 of it that we're interested in. So 3.3. Let's see, part 15. Okay, here it is, Gramian product. So when we were doing that, part 5 we're interested in, says A transpose A is a full rank. A transpose A is square, of course, if and only if A is a full column rank. All right, well, we had full column rank for matrix L. L is n by R as a full column rank matrix. Okay, so by Theorem 3.3.14, part 5, if we'll consider L transpose L, that's a full rank matrix of rank R. It's an R by R matrix. What's up with matrix R? Matrix R is a full row rank. Okay, I need full column rank, so let's consider R transpose. If R is a full row rank, then R transpose is a full column rank because the columns of R transpose are the rows of R itself. So we can apply that same result to the R transpose matrix. So we'll take that matrix, R transpose, and transpose it, multiply by that matrix, R transpose. So we get R transpose transpose times R transpose. Same format that we've got here. Right, except we're taking a matrix that's already transposed and then doing this type of product. Okay, that matrix, R transpose, transpose, R transpose, R times R transpose, in other words, is a full rank matrix R, of a full rank R. And it's a square matrix as well. All right, so we've got two full rank matrices, L transpose L and R transpose. Well, if they're full rank, then they're invertible. So let's take a product of those two matrices, L transpose L times R transpose. If both of these are invertible, then the product is invertible. All right, we're trying to get to matrix A drug into the conversation somewhere. We're getting closer. Let's associate the L and the R here. Hey, matrix A equals L times R. So by making that association, we can replace that with A, getting the matrix L transpose A R transpose. We can claim this is invertible because we know each of these are invertible, and so the product of these two is invertible. Product equals that, so that's invertible. All right, good thing, because we're going to have that apparently in the pseudo inverse of matrix A. All right, so define matrix B to be R transpose times the inverse of what we were just looking at. We know that to exist now, times L transpose. Okay, all we got to do is take that, and so this is established that that is well defined and exists in everything. Invertibility is the main concern. All we got to do is show that B satisfies the 4 parts of the definition of pseudo inverse, and that's just computational, and that part of the proof's left as an exercise. So indeed, this thing B is a pseudo inverse of matrix A once those computations have been processed. So that gets you the existence of a pseudo inverse of a matrix A. How about Theorem 3.6.3 about the uniqueness of that inverse. So that's the claim here. We'll simply suppose there's two and show they're equal. For matrix A, the pseudo inverse of A is unique. All right, we already addressed what happens with the zero matrix. It was unique. Its inverse is the appropriate size zero matrix. So take A to have positive rank, and suppose both of these are inverses. Suppose B and C are both pseudo inverses of A. We're going to show B equals C. All right, let me get it in front of us. We need the definition of pseudo inverse. Okay, 3.6, definition of pseudo inverse was this. Okay, matrix times its pseudo inverse times matrix equals matrix. Pseudo inverse times matrix times pseudo inverse equals pseudo inverse. Little relationship between those two. Pseudo inverse times matrix is symmetric, and matrix times pseudo inverse is symmetric. All right, so these are the four rules we're playing by. These are the four things that would have had to have been justified at the end of that previous proof. But we're going to use those four things to computationally show matrix B, assumed to be a pseudo inverse, equals matrix C, assumed to be a pseudo inverse. Okay, matrix B equals B times A times B. That was property 2. That's pseudo inverse equals pseudo inverse times matrix times pseudo inverse. Think of these as little A negatives, and that's exactly what property 2 said. All right. Hey, B times A, pseudo inverse times A, equals pseudo inverse times A transpose. That was the symmetry part. Pseudo inverse times A is symmetric. It's property 3. So we can put a transpose on this BA thing, and we get equality. We can take that transpose and apply it to the product the usual way, right? This is A transpose B transpose B. Let's see, matrix A can also be written as A, C, A. That's matrix times pseudo inverse times matrix equals matrix. That was the first property. We've hypothesized that C is a pseudo inverse. Maybe look back at it. So we should see in property 1, A super minus A equals A. So we're taking A within that transpose and replacing it with A pseudo inverse A. It's okay. So right, that's what property 1 reads. A pseudo inverse A equals A. That's what we've got, except the pseudo inverse we're denoting with a C at this stage. Okay. All right, ACA equals A. Oh yeah, that's happening inside a transpose. All right, that's a substitution. Now we can take the transposition on this product, write it as A transpose, C transpose, A transpose, you know, write them in the reverse order. It's hard to see because of the symmetry in that little product. Let's see, A transpose, C transpose is the same as CA transpose, property of transposes. Reverse the order and insert the transpose, maybe read it from this side to that side. So that gives us this particular product. Okay, the CA transpose, that's a pseudo inverse times A. We know those to be symmetric. You can drop the transpose. Transpose is gone. Still got a transpose on the A. So it's a little step-by-step manipulations to move the transposes around mostly. All right, symmetry. Property 3 gave us a symmetry, says you can drop the transpose there because we got a symmetric matrix there. Okay, let's take this A transpose, B transpose, rewrite it as BA transpose. Right, you see just moving things back and forth and then using symmetries to get rid of the transposes. Hey, BA, that's a pseudo inverse times A, exactly like what we had up here, different pseudo inverse, allegedly different. BA, pseudo inverse times A, is symmetric, so the transpose equals the matrix itself. So we can drop that transpose, symmetry property 3 again. And then we can reassociate some things. Let's see, let's associate the A, BA. A, B, A pseudo inverse A pseudo inverse A. That's A itself. That was property 1. Okay, so we've got B equals CAB down to this stage. We're trying to get C out of this. It says pick up where we left off. CAB, the last thing we had. B equals this. Okay, let's take matrix A, and effectively we've introduced a C. We got to get rid of this B. So the remainder is to get rid of this B. We're going to take matrix A and write it as ACA. We're about halfway there in terms of getting to C. That was the first property of a pseudo inverse. A pseudo inverse A equals A itself. So we've made that substitution. Let's associate the A and the C. Okay, I don't know what's going to happen next by now. It's the same thing we did before, now with a C instead of the B's. So, hey, AC, A times a pseudo inverse, that's a symmetric matrix. It equals its transpose. So we can put a transpose on the AC, take that transpose over the product, write it backwards with transposes, so we get a C transpose A. We used, let's see, we used the symmetry property in getting from here to here. That's what's being justified. Okay. Hey, if we've got A times a pseudo inverse, that's symmetric as well. So we can put a transpose on the AB. AB is symmetric. A pseudo inverse of A is symmetric. So we can put a transpose on there. First part remains the same. All right. I want to view this as a product of two transposed matrices, matrix A and matrix A times B. All right. Hey, when we got a product like that, we can take that as a transpose of the product. So we can take AB times A, AB times A, and transpose that. View AB is the first matrix here. So when we took the transpose, we'd have an AB transpose second, correct? And we'd take this matrix A, transpose it, and it would appear first. So yeah, that's just that part of the equality. That equality is just properties of transposes of products. Why would you want to do that? Hey, A pseudo inverse times A, that's A itself, property 1. So we can take the ABA, rewrite it as A, it's still inside the transpose. Okay, we got a product of two transposes. Do your thing with transposes again, reverse the order, put the transpose outside, say, hey, wait a second, that's A times a pseudo inverse, that's symmetric. We can drop the transpose to get the AC, and we've got CAC. That is, by property 2, pseudo inverse. We got pseudo inverse times A times pseudo inverse equals pseudo inverse. We'll check that in a second. So we've shown B equals C, and we've shown that if B and C are pseudo inverses of A, then they're equal. That is, pseudo inverses of a matrix are unique. Let's see, and I wanted to double check. Pseudo inverse times A times pseudo inverse equals pseudo inverse. Pseudo inverse times A times pseudo inverse equals pseudo inverse. So that was the very last step that we had in that proof. All right, so pseudo inverses always exist, and unlike generalized inverses, they're unique. And that's the little comment here, along with the fact that, hey, if A is invertible, you know, these pseudo inverses are unique. The pseudo inverse must equal A inverse when it's unique. All right, I take some inspiration from systems of equations. Suppose we've got a pseudo inverse of A, and we consider X equals a pseudo inverse of A times B. I'm expecting it to behave like A inverse. The claim is this is a solution to the system of equations AX equals B, because if we substitute it in, poof, we get a solution. So suppose AX equals B. We know that A pseudo inverse of A times A equals A. That's the first property of pseudo inverses, first part of the definition. So we can take AX equals B and replace the A with the A pseudo inverse times A. to get this. We can associate the A and the X, All right, we know AX equals B, this is what we're dealing with. So we can substitute for AX, B, then we can associate these two, the pseudo inverse in B. We get A times this thing here equals B, then this thing here, highlighted, that's a solution to the system of equations. So pseudo inverses give solutions to systems of equations. Generalized inverses did as well. A tiny bit of history on this. It's got Roger Penrose's name associated with it. The four properties in that definition of pseudo inverse are called the Penrose Equations. Roger Penrose, he's more of a physics than a math guy, but he showed that every finite matrix with real entries or complex entries need some slight tweaking in terms of the complex entries. The symmetry properties have to be replaced with conjugate symmetry if I have complex entries in the matrices. Not a problem. We're only real entries in here, but slightly different in the complex setting. So Roger Penrose shows every finite matrix, real or complex, has a unique pseudo inverse satisfying those four equations. Does so in 1955. So the idea was also addressed in 1920 by Moore. That's the reason these are called the Moore-Penrose inverses, in addition to being called pseudo inverses. I mean, pseudo inverses is a mouthful, but I think I prefer to use that over Moore-Penrose inverse. Apparently Moore, publishing in the Bulletin of the AMS, a little bit more of a math guy than Penrose is, publishing in Proceedings of the Cambridge Philosophical Society. So it could be anything. Penrose's names, we'll see, is more likely associated more with physics stuff. C.C. McDuff apparently was the first to give the formula in Theorem 3.6.2, that thing where we had the L's and the R's and the L transposes and the R transposes, the formula for a pseudo inverse of a given matrix. So this apparently dates from 59. And it's a little bit easier for us just to take the formula and show it verifies those properties. It's odd that it wasn't done that way originally. These little historical comments I found, I've mentioned this reference before, Generalized Inverses, some book I found somewhere online that gave a little bit of the history of it. Roger Penrose, the old dude, was born in 1931. As of today, so I'm in summer 2020. He's an emeritus member of the Mathematical Institute at the University of Oxford. He did his PhD work in algebraic geometry, but this sort of trickles down more to interacting with Stephen Hawking and the theory of black holes. It's Hawking and Penrose that show that a black hole collapses to a singularity of infinite density and zero volume, something freakishly wrong if you're a fan of quantum mechanics. I say if you're a fan of physics, infinite, anything physical that's infinite, I got a problem with. Maybe that's just me. But here's a picture of Penrose. His faculty website is still active as of today, or this era, summer 2020. So that takes care of a couple of different ideas about inverses, generalized inverses, and pseudo inverses. And we'll move on to a new property of matrices called orthogonality in the next section. So onward and upward. Have a nice day.